Hello everyone, welcome to this video tutorial on modal analysis in Ansys Workbench. So these are the learning outcomes of this video. After this video lecture, you will be able to perform a modal analysis in Ansys Workbench. You will be able to extract the mode shapes and corresponding natural frequencies for 2D structures. So this is the problem statement. We have to determine the prominent natural frequencies of the structure in x, y, and z coordinate directions. So the problem or the geometry or the structure we are going to consider for this analysis is the Eiffel Tower. We are going to construct a 2D sketch of the Eiffel Tower and will provide the cross section, will prepare the cross section, a square cross section for the Eiffel Tower links, and then we'll perform the modal analysis or natural frequency analysis for this type of structure. Okay, so let's move to the workbench. Now we'll go to the workbench, and after that we'll select modal analysis. You can see here modal analysis using mechanical APDL solver. Now here we are not going to change the material properties, that is engineering data will be going to be same, and we'll start modeling the geometry. Now as we don't know the actual dimensions of this sketch, we are going to consider or we are going to consider some approximate dimensions for the geometry. Okay, once again we'll see this is the geometry. There is a circular arc, then we'll consider these as a rectangles. This is a rectangle and this is a rectangle of different shape, and we'll join this with the lines. Okay, so let's delete this. Okay, so we'll move to the sketch. Okay, and the first step is to create a layout sketch. Okay, we have to take this to create a layout sketch. Then we'll move and set some units. Okay, this is how you can set the units. We'll keep the units in millimeters, or first of all I'll change it to the meters for better understanding of the structural dimensions, and I'll select the XY plane, and we'll make the plane perpendicular or parallel to the screen. Okay, so we'll start modeling with a circle. We'll prepare the circle of 0.5 meters. Okay, so this is the circle we are going to use, and some lines 0.2 meters, and from here also we'll make 0.2 meters. So total horizontal height will be 0.2 plus 0.2 plus 0.5, that is 0.9. We'll trim this half of the portion. Okay, then we'll prepare some rectangles here, and what I will do, I will make this rectangle symmetric about this line. So we have to select this symmetric constant. We want this to be the line of symmetry, and these two should be symmetric about that line. So this is the symmetry constraint. Now we'll give the dimensions to it. is the radius 0.25. I'll increase the font to 5. Okay, then this dimension is 0.2, this dimension is 0.2. Okay, now we want this rectangle to be less of less width, so we'll decide this will be 0.75. It's looking good. Yes, it is looking good. Then the height from this base, this should be 0.3. Okay, and this height of the rectangle is 0.2. That is too much, so I'll somewhat decrease it by 0.1. Increase it to 0.1. Okay, so this is looking too much small, so I'll increase it to 5. Yeah, that looks good. Now we'll join this 2 with line. Okay, and we want this line similar from this side also, so we'll use the mirror constraint. Click on mirror, then click on this line of symmetry and click on the line what we have to mirror. Okay, so this is the base we have constructed. Then we'll move to the new rectangle section. Now first of all we will decide the dimensions of the rectangle. Yes, this is what we want. Then this should be less than 0.75, so this could be 0.55, and we want it to be symmetric about this line. Symmetry, this line and this line will automatically become symmetric. Okay, now what we want this height to be 0.5. Okay, then we'll join this. Okay, we want it to be somewhat like this. Change some angle, zoom it here, go close to this, and yes, want to change the angle, we can change the angle like this. Now use the mirror constraint here, mirror about this, what you want to mirror this. Okay, now we'll get the third rectangle, so decide the dimensions. 0.1, 0.1, 0. 0 point. So we have to decide this less than 0.55. Let's do it 0.35 and let's see what happens. Yeah, it looks good. Then prepare this symmetry constraint. So whenever you select this symmetry, first of all you have to select the line of symmetry, then these two should be selected to make the whole rectangle symmetric about this line of symmetry or axis. Okay, then total height we have to decide. From this to this should be, we'll make somewhat extra. Now this should be 0.75, and okay, we'll see how does it look like. I'll make it 1 meter. Yeah, Now it is looking good. Okay, so again we have to prepare the same mirror line. We'll go to mirror, select the plane of mirror and line which we want to mirror. Okay, that's done. Then at the top we want just structure like this, create a mirror of this line. Okay, and then join these two endpoints. That's it. Okay, okay, then what we'll do, the height, we'll keep this as a 0.12. Okay, no offense to these dimensions. So that's our Eiffel Tower. We'll end the sketch. Then we'll go to prepare the profiles and we'll select this rectangular profile. Now leave about this error, that is not going to matter us. Okay, I'll clear all the errors. So the next thing is we have to prepare the rectangular profile. Before that I will switch to millimeters. Okay, because this profile has to be created using mm's. Edit, and this is 10 mm by 10 mm. So if we consider it is 1 centimeter cross 1 centimeter rectangle. Okay, that's good, because our Eiffel Tower, the height of our Eiffel Tower may be 500 plus 600, 1100, that is 1 meter, 1100 mm. Okay, then this is total 2100 mm plus 122 mm. So 2222, 4 times 2 meters mm's. So 2 meters height is there. And if we consider the rectangular cross section of 10 mm by 10 mm, that is sufficient for this thing. Okay, so we have modeled this rectangular profile. The next task is select all these lines and apply this profile. Okay, now you can see here we have applied this profile. Next task is select all these beams, and make new component. So we have prepared a new component. After preparing the new component, move to the workbench and share topology. So you can see here we have found 30 vertices. Now we'll click OK. So we are sharing the topology. That's it from geometry modeling. Okay, then we'll move to the workbench again and we'll go to the model, that is Ansys mechanical. We'll start the Ansys mechanical. It is saying that starting mechanical. Okay, yeah, so here we are in Ansys mechanical workbench. Let it open completely. Yeah, so we can see a geometry here, the basic shape of Eiffel Tower. Okay, then what we will do, we'll mesh it. Then we'll see the thick shells. So this is how it looks like in 3D. If you want to see 3D, this is how it looks like, a 2D structure with the square cross sections of members. Okay, then the next thing is, that's very important from the modal analysis respective, you have to click on this analysis setting, and you have to set the number of modes you want to find. Okay, maximum modes you want to find. So here you can uh, calculate any number of modes. Maximum you can find any number of modes. Let's say 6. I can set 6, I can set 10, I can set 20, I can set 25. So here I'll be setting it to 25. Okay, so I'll calculate the 25 number of modes, and after that we'll click on solve. So it is solving this mathematical expressions and all, and yeah, we have these settings. Okay, so the first three modes we got as a 0 0 0. Okay, because we have not given this boundary conditions, given the boundary condition, and this type of modal analysis is called as free modal analysis. So as we have not given the boundary conditions, this becomes free modal analysis. Now you can see here, though we have not given the boundary conditions, we got the modal shapes. Okay, now we'll go to the solution. I'll go to the solution, and we have to look for a table. So which table we have to find out? We have to find out a participation factor calculation table. Okay, so we have to find out the participation factor table. So in this participation factor, if you want a if you want a natural frequency which is prominent in x direction, you have to look for a effective mass column. So in effective mass column, you have to find out the maximum entry. So this is the maximum entry, and if we see the ratio here, it is 1. So if we see in participation factor calculation in x direction, we have mode number 6 where ratio is maximum or 1, and we have maximum effective mass amount here, that is 6.5, which is way more than this all the values here. So we'll go to the mode number 6 in solution information. In solution we'll go to mode number 6. So this is mode number 6, and we'll create a mode shape result for this thing, and then we'll evaluate result. Now this was about the axis x, or along the axis x. So the movement should be along the axis x-axis only. So to see the movement along the x-axis, we have to make this arrangement. Okay, and we'll see. You can see here, this is a free analysis, so this is moving in a x direction. Now we'll go to the solution information, and we'll see the y direction, and the mode number 4. Here we are getting the ratio is 1, and effective mass is 6.98. Here also the effective mass was 6.56. Okay, so we'll move to the mode 4. And this mode 4 will generate mode shape results. Okay, and this will evaluate, and now this will be freely moving in y direction. Okay, you can see here, this is freely moving in y direction. So first 3 modes are completely 0, and 4 5 6 is 10 raised to power minus some value 10 raised to power minus 5, which is nothing but 0. So if we have free analysis, this will also will fetch the results, create a mode shape result, and we'll see this will be along the z direction, I think so. So you can see here, this is the rotation about y. We'll see the z direction, it is mode number 3. It's mode number 3, prominently it's mode number 3. So I took this the wrong, You have to go to 3 and you have to create the mode shape result, so it will be showing the free translation along Z direction. You can see it, so it is freely moving in Z direction. So the first 6 we have to leave because these are zero frequency modes, as this is nothing but the rigid body movement. Okay, so if we want a, better results, we have to provide the actual boundary condition. And I mean in me actual boundary condition means this should be fixed at the base. So we'll stop this first and we'll go to the model and we'll insert the fixed support here for this and this link, and we'll apply this. Okay, now you can see here I'll delete all these results. Yes, I don't want this. And now we'll solve it once again. Now this is fixed free condition. We are fixing here at the bottom, and other rest of the part is free. Now we have the mode shapes here. Okay, you can see I have calculated 20 mode shapes and there are no zero values here. Now we'll go to the solution information and we'll check the participation factor calculations. Now participation factor calculation in x direction, we have to see the ratio 1. Here we are getting the ratio 1, and this is mode number 4. Now we'll go to the solution, we'll go to the mode number 4. Okay, and we'll evaluate the results for this thing. I'll also rename this x direction mode 4. Okay, so this should be x direction. So if you want the deformation in x direction, you want to see the deformation in x direction, you can see this. So you can clearly see this, the movement is in x direction only. Okay, now you can see there is no movement in z direction, and this also clearly shows that there is no vertical movement as well. So this is the pure uh, natural frequency in x direction, or prominent natural frequency in x direction, mode number 4. So this is the natural frequency 10.755 hertz is the natural frequency of the structure in x direction, which is most prominent in x direction. Okay, now I will go to the y direction calculations. I will see the ratio mode number 11. So mode number 11 will evaluate the results for 54, create the mode shape results. So as this was the y direction, it should elongate vertically upward. Okay, and I'll rename this y direction mode was 11. Okay, so and we'll evaluate the results. We'll see. Okay, so you can see here it is moving upward in y direction. Now if you want to see x direction movement, there is no x direction movement. If you want to see z direction movement, there is no z direction movement. So it is purely a mode which will excite the structure in y direction at frequency of 54.839 hertz. Okay, so we'll move to the next table, participation factor calculation for z direction, and we'll see the mode number 1. So we'll go to the results and we'll evaluate this as a z direction mode 1. Okay, we'll evaluate the results. Okay, and you can see now Now you cannot see much more deformation in x and y directions. You can clearly see there is no deformation in x and y direction. To see this deformation, we have to change the view, and you can see this is vibrating along the z axis. So these are the three prominent modes of vibration, and the corresponding natural frequencies, that is for z direction is 1.2209, for x direction it is 10.755, and in y direction it is 11 number, so that's 54.839. Okay, so these are the most prominent modes in all these respective directions. Now there could be a chance that this structure may rotate, may rotate about any of these axes. We'll go to the next table, participation factor, rotation about x. Now if we consider a rotation about x, which is nothing but the translation about z, you can see here, we are getting for rotation about x, we are getting the ratio 1. Okay, I will move to the next ratio y, about rotation of y, the mode shape is third mode. Okay, so we'll go to the solution, we'll evaluate the mode shape results for rotation about y. Y mode 3. Now we'll evaluate the results. Now you can see this is rotation about y. Now we'll see this rotation, we can see this rotation in xz plane. So this is the structure is rotating about the y axis. Okay, now the same case we can find out for rotation about z axis. Okay, so rotation about z axis, we are getting the ratio for mode number 4. Okay, so rotation about z axis is nothing but a translation in x, and rotation about x axis is nothing but translation in z. So this is the mutual rotation and translation. Okay, now if we see any other mode, if you want to see any other mode, there is no ratio near to the value of 1. Okay, so this is how you can calculate the mode shapes and the corresponding natural frequencies and the results using Ansys Workbench. And you might have understood the concept of participation factor and ratio, how to use it to calculate the prominent modes in respective directions. Okay, so that's it in this video. These are the results. You can copy the results, as you know, from the results and images. Copy to image to clipboard, image to file, image from file, and you can create the reports. Okay, so thanks for watching this video. I'd like to request you to share, subscribe, and like to the video. Okay, kindly subscribe to the channel also. Thank you.